right, so this is Math 150, Section 2, 2021, Multivariable Calculus. This is the chain rule lecture. I'm rewording numbers a little bit, so this is lecture 10, but it might be now listed as number 11, so I'm switching things up because of the new calendar. Today is the chain rule. This, yes?
On below, I think it says that the next lecture video is Monday, even though it's usually that still, so we're supposed to wrap up or something.
No, I'm going to change that.
Okay.
I wasn't used to, this is in fact related to the I have to change things now because I didn't realize that reading period was changing this early. So I will be adjusting things. So what is the chain rule? To some extent, it is the worst material of the semester. It is the most theoretical, the most involved, but there's some beautiful formulas for it. And it's not so bad to use if you just go through it methodically. It's very similar, not surprisingly, to the rules for differentiation. If you just keep going through and writing everything down and carefully substitute, it's not that bad. The more steps you try to skip, the worse it's going to be. So earlier today, there was some questioning as to whether or not I did a differentiation correctly. Turns out I actually did. I've been doing this longer than you've been alive. I should be able to do this quickly in my head. I will show you slower ways to do it that minimize the chance of making a mistake. So in the video, it talked about trying to build some intuition. So maybe we have A equals f of g of x. And the goal is to start off with some functions f and g where we know what the derivatives are and see if we can use that to sniff out what the derivative of a of x should be. So maybe f of input is 3x to the 5th plus 1. G of x is x squared. So if I look at f of g of x, that's going to be f of x squared. That's going to be 3x squared to the 5th plus 1. That's going to be 3x to the 10th plus 1. Is it going to be hard for us to differentiate this? No. And then we can try to figure out, once we take the derivative, how do we relate this to the values of f prime and g prime, and f and g? I could switch things. I could say maybe f of x is x squared, and g of x is 3x to the 5th plus 1. And if I do that, now f of g of x is going to be f of 3x to the 5th plus 1. So that will be 3x to the 5th plus 1 squared. Well, I can square things. It will be 9x to the 10th plus 6x to the 5th plus 1. Can we differentiate that? Yeah, not a problem. And so we can use this to try to build up some intuition. And in the end, we get, it looks like a prime of x is f prime as g of x times g prime of x. And we talked in the past about why this is a reasonable formula. F prime should be evaluated at g of x. It makes sense that f prime and g prime have some role to play in the chain rule. We talked about why this is changing our speed and going through this fast. We then talked about what does the multivariable chain rule look like. And we started off with a very special case. We had function g from R to R3 and f from R3 to R, and then some function a, which would be from R to R. This was a of x was f of g. Actually, I think we used 2. F of g of 2. And I sometimes use c of t or g of t to just remind myself that I have some curve in space. And so I might write that as x of t, y of t, z of t. And we calculated what the chain rule should be in this special case. And again, this is nice. A is a function of just one variable. Now, in one variable calculus, it turns out there are 3 different definitions of the derivative. One is the standard, the limit as h goes to 0. One is the limit as x goes to a. And one involves the limit of subtracting off the tangent plane approximation, and the tangent line approximation. So we have h going to 0, x going to a, subtract off the tangent line. Which do you think generalizes best to several variables? The tangent line. That's the one that we use as the basis of our definition of the derivative. Is we looked at the tangent line. And we saw that the way to view the tangent line is if I give you a function at some point for it to be differentiable, it means the tangent line is doing a tremendous job approximating. That locally, you look like a straight line. And so we used this to study what is f of c of t. Remind myself that's okay. And that was our function a of t, and we wanted to figure out what the chain rule would be in this case. So what would that be? Well, we would have f of c of t plus h, that should basically be approximately f of c of t, where we stopped, plus the gradient of f at c of t times c of t plus h minus c of t. This is a dot product because we have vectors. And we saw this was a really good way of viewing what happens in a small amount of time if we shift forward in time a little bit. Well, where do we think we are at time t plus h? Well, we started off at time t at c of t, so we had a value of f of c of t. That's where we started. The grade of f is telling us how fast f is changing. It's pointing in the direction of maximum change. And then this is our change vector. And so this dot product tells us how much I'm changing in the x direction times the movement in the x direction, plus how much I'm changing, how fast I'm changing in the y direction times the y change. If I look at c of t plus h minus c of t, and I divide by h and multiply by h, it looks a lot like a derivative. And if I look at this component by component, it's x of t plus h minus x of t over h, something for y, something for z, times h. That's what the change vector is looking like. C is just x, y, z. And so if I move forward a small amount of time, this is looking like x of t plus h minus x of t over h times h. I've just multiplied by 1. So much of math is doing the algebra to try to illuminate what the expression was. Well, as h goes to 0, what is x of t plus h minus x of t over h? What does that converge to? So what will that look like? So as h goes to 0, x of t plus h minus x of t over h looks like which slope? There's a nice name for x of t plus h minus x of t over h as h goes to 0. So the limit as h goes to 0, x of t plus h minus x of t over h. What is that equal to? The derivative. Be more specific. Which derivative? The derivative of x. Be even more specific than the derivative of x. The derivative of x where? T. This looks like x times t, or dx dt because it only depends on one variable, or if I want to be really careful, partial x, partial t. To some extent, I don't really need to say partial x, partial t, because x depends on only one variable. But if I write it like this, it's going to make it a little bit more clear how to generalize. And so the change vector here is going to look like df dx at c of t times partial x partial t plus df dy at c of t dy dt plus partial f partial z at c of t times dz dt. And these last ones are all evaluated at time t. So that was the chain rule we had before in the special case when G had just one input. Well, we could extend it to allow G to have more than one input. Right now, If G had another input, just imagine that that's a 1 for the value. All that would change is every calculation would be the same, except over here I would have commas. I would have x of t plus h comma u. So we often use u and v for the two variables. So I can have maybe g from R2 to R3, f from R3 to R, a from R to R, and maybe a of u comma v is f of g of uv. The book sometimes uses notation, doesn't really put in this extra function g. I like to put it there to remind myself it's the chain rule and to remind myself where to evaluate this. As we go through the calculation, it's very similar to before. You look at f of g of u plus h g. So I'm trying to calculate the partial of a with respect to u. I'm keeping b fixed, and I'm increasing u by a small amount. Well, let's try to guess what we think this should be. What do you think this point should be close to? What do you think this value should be close to? We have f of g of u plus h of v. This should be approximately remember, h is a really small number. F of g of uv, right? If h is really small, then it should be essentially what we started at. And now we want to add the change. So we do the gradient of f at g of uv dotted with the change vector, g of u plus h v minus g of uv. It's extremely similar to what we had before. And if we expand all of this out, what is g of u plus v, u plus h comma v minus g of uv? So g of u plus h v minus g of uv, divide by h, multiply by h, is going to just be x of u plus h v minus x of uv over h, blah, blah, the other coordinates, times h. Very similar to what we had before. So here, the g of uv is just x of uv, y of uv, and c of uv. Very similar to what we had before. So we plug this in, g of uv is just x of uv, y of uv, z of uv. So the change is going to be df dx at the point g of uv, du or dx du, and this is at the point of uv. My hand is beginning to hurt from doing this lecture twice. And that's why a lot of times we just ignore and we just don't bother writing at g of uv or at uv. Because it should be clear from context where you're evaluating things. It's better to put it in. The next piece would be df dy at g of uv, dy du at uv. And then the last would be df dz at g of uv, dz du at uv. And this is just the partial a with respect to u. How would you find the partial of a with respect to v? What would we do if we wanted the partial of a with respect to v?
Same thing, but all the u's.
Yeah, all the u's down below would be not a big deal. So the derivative of a, the gradient of a grad of A, all these different ways of writing it. It's just partial A, partial U, partial A, partial B. Because A involves two variables, its derivative has two components. If it had 5 variables, how many components would it have? 5. And so this is going to be a monster formula for the derivative. So all the lectures to have people at home, this is the worst one because you want to keep this on the screen throughout the entire lecture. So it's going to cut down a little bit on our board scale. Hopefully from the email we just saw, this is the last semester we're going to have this happen. So we'll try to keep this up as long as possible. If you think about it, dA du, well, dA du should be related to derivatives of f and g. I'm viewing my g as really x of ub, y of ub, z of ub. If you want to, you could almost do this as if you want as g1 of ub, g2 of ub, g3 of ub. There's lots of different language you can use. I like to use x, y, and z because I'm viewing my function f as a function of x, y, and z. So to figure out how A changes with respect to u, I find how is f changing with respect to x, y, and z, and I then take into account how x, y, and z are changing with respect to u. So it's a very natural formula when you think about it. Can I just cancel the dx's? No. In fact, I deliberately chose this problem because f has 3 inputs, not 2. It makes no sense to talk about the partial of f with respect to u. F doesn't have just 2 inputs, it has 3 inputs. Okay. So this is the theory of the chain. Any questions on this? Right, it is now time for a monster calculation. So I will do the same example that was done in the video. When you look at this example, it should be immediately clear that we do not want to use the chain rule. Why are we doing this example then? Well, when we're trying to understand if something works, it's nice to know if we have the right answer. So if you can ever calculate something 2 different ways, if the 2 different ways match, does that mean you got it right? Sadly, no. Not necessarily. But you have a little bit more confidence. What if they don't match? What do you know if they don't match? Good, at least one is wrong. You sadly don't know that at least one is right. You know that at least one is wrong. Maybe you have 2 completely different wrong answers. Too soon to tell. When I was in high school, I took a physics class at Harvard. As a Yale man, I have no problem that Yale did not consider that a real class towards graduation. And on one of the exam questions, I got full credit, even though I made 2 mistakes on the problem. The 2 mistakes canceled. So if you do integration by parts, for example, if the boundary term vanishes, then you have negative times an integral. And then if you do an integration by parts again, you get another negative times the integral. If you could get that negative sign, but the boundary terms vanish both times and you do integration by parts twice, then you have the right answer. Yes? I made a mistake similar to that, where the mistake canceled later on. And when people are just checking, well, the only way they could get this strange answer is if everything worked out properly, so they must have done all the work right. Just because you have the right answer does not mean you've done the right work. So if you can check something in more than one way, that's great. So let's consider polar coordinates. So what is x of r theta? How would we write x and y in polar coordinates? R cosine theta and r sine theta. And I'm going to let f of xy be the function x cosine x squared plus y squared. And so my function g of r theta is x of r theta, y of r theta. And so what is f of g of r theta. This is going to be f of r cosine theta, r sine theta. All right, so it's x, which is just r cosine theta. And then we have cosine of x squared plus y squared. What's x squared plus y squared in polar? R squared. So it's r cosine theta cosine of r squared. This is a terrible problem to differentiate. No, this isn't too bad. So a of r theta is r cosine theta cosine of r squared. Which derivative would you rather do? The derivative with respect to theta or the derivative with respect to r? Or does it not matter? Is one derivative easier than the other? Yeah, theta is much easier because I only have theta occurring in one spot. I have two r's. What am I going to have to use for the r derivative? So what rule will I have to use to do the r derivative? I'll have to use the product. And in the midst of doing the product, I'm going to have to take the derivative of cosine of r squared. What rule will I have to do for cosine of r squared? Chain. So clearly the theta is better. dA d theta, the derivative of cosine theta is minus sine theta. It's going to be minus r sine theta cosine of r squared. So partial A, partial theta isn't too bad. Let's calculate the derivative of A with respect to r. So I can pull out the cosine theta, because it's a constant. And then I have the derivative with respect to r of r cosine r squared. And what I'm going to do is I'm going to just show you how to do this problem very slowly. I know it's been a while since some of you have done differentiation in a way that will minimize your chance of making an error. So at the end of the day, we'll get that it's cosine theta, and then the derivative of this, the product of the derivative of r is going to be 1, so it'll be a cosine of r squared, then r times the derivative of cosine of r squared, which will be negative 2r, will be a negative 2r squared cosine of r squared. So this is the fast way of doing it, not writing anything down, just doing it in your head. Here is the slow, methodical way that guarantees you will not make a mistake. So let's say I want to take the derivative of v of r times c of r. So the product rule says it's going to be v prime of r times c of r plus v of r times c prime of r. And the goal is to just write down everything and then just keep substituting. So what would v of r be for our problem? R would just be r. And what would c of r be for our problem? Cosine of r squared. And so now v prime of r is just 1. C prime of r, root of cosine is minus sine. And then I'm just going to do the derivative of r squared in my head as 2r. If you weren't sure, the slower way to do it is minus r, minus sine squared r times the derivative of r squared, just write it like that. And then just take an extra step. It's very slow. If you think this will just be negative 2r sine of r squared. And now I have everything I need to substitute in. So this is a way to make sure that you minimize your chance of making a mistake in doing the product. Is write down the formula. Why am I using B and C and not A and B? Do I not know the alphabet? We've already used A. I don't want to overload a symbol. And I can't use F and G because I've already got an F in the problem. So I'll just use B and C. I'll use the next letters that are available. If you wanted to, if you were having trouble with this, you could say, well, let me write C of R as D of E of R, and then C prime of R is D prime at E of R times E prime of R, and then start writing down what is D, what is E, what is D prime, what is E prime, and use that to substitute here. So whenever you have a complicated problem, you can keep breaking it up into smaller and smaller parts. So any questions with how we got this? Was it bad to calculate partial A, partial R? No. Now let's do the nightmare of the chain. Okay? And the purpose of this is to illustrate that for some problems, it's better to just substitute directly. You cannot always do that. One of the standard examples where you can't do that is imagine you have a balloon that you're filling up and the radius is expanding, and maybe you're told at a split moment in time, the radius is expanding at 1 centimeter per second. And you want to figure out how much is the volume changing. If you want to substitute and take the derivative, you might need to know all the different values of things. And I don't have the functions to take the derivative. I know at a certain point how something is changing. And so the chain rule will become very useful for that. If I know how something is changing at this point, great. And I can bypass having to do the full substitution. All right, so now let's calculate dAdr the long way. dAdr is dx at g of r theta times dx dr at r theta plus df dy at g of r theta times dy dr at r theta. Do we agree that that is the derivative of A with respect to R? And now we have to substitute. So there are 4 things we need to find. In order to try to keep as much on the blackboard, I will just write some of the derivatives over here in this beautiful rectangular box. Okay? X is equal to R cosine theta. So what's dx dr? So if x is R cosine theta, dx dr is just cosine theta. And I should be writing that I'm evaluating this at R theta. It's clear that I'm evaluating this at R theta. To be really explicit, dx dr at the point R theta is just cosine theta. What about dy dr at R theta? So y is R sine theta. So dy dr would just become sine theta. We're halfway there, right? We have dx dr and dy dr. Great. So these, the dx dy, these are the ones that are evaluated at g of r theta. The others are evaluated at r theta. So now we have to calculate the derivative of f at x, and then evaluate that at the point g of r theta. All right? Let's look at df dx. So f of xy is x cosine x squared plus y squared. So what rule do we use to take the derivative? Product rule. So the derivative of x is 1. We get 1 times cosine x squared plus y squared plus x times the derivative of cosine x squared plus y squared. What's the derivative of cosine of x squared plus y squared? It's negative sine x squared plus y squared. It's negative sine x squared plus y squared. And now I take the derivative of x squared plus y squared with respect to x, which is going to give me 2x. So when the dust settles, df dx is cosine x squared plus y squared minus 2x squared sine x squared plus y squared. If you're having trouble with this, just do the product rule and write it out again very slowly. You can use maybe B and C, or where I've already used B and C, so maybe I'll use D and E. Okay. Any questions on how I take DF/dx? Have I evaluated DF/dx where I want to evaluate it? Is this where we want to evaluate DF/dx? Where do we want to evaluate it? I want DF/dx at what point? Not at R theta. G of R theta. And so when I put that in here, that's the point R cosine theta, R sine theta. So the first piece, what is this going to be at R theta? At G of R theta, what's x squared plus y squared? R squared. So it's going to be cosine of R squared. Now we have minus 2x squared. So that's going to be minus 2r squared cosine squared theta sine of R squared. If anybody is enjoying this relative to the direct substitution, we need to do an intervention. And email me, we will arrange a time. Okay? This is not pleasant. And we're not even done. And for those of you in the audience who are not enjoying this, this is the second time today I've had to do this proposition. Okay, it could be worse. What do we have to compute now? What's left? df dy. Unfortunately, df dy is much easier. df dy, the only y dependence is here, so it's going to be x. Derivative of cosine is negative sine x squared plus y squared. Derivative of x squared plus y squared is going to be 2y. So it's going to be negative 2xy sine x squared plus y squared. So what is df dy at the point G of R theta? So what's xy going to be at the point R cosine theta, R sine theta? So we're evaluating it at x R theta, y R theta. So this is just the point cosine theta, R sine theta. So what is x times y going to be when x is our cosine theta and y is our sine theta? Negative 2r squared cosine theta, sine theta, sine of r squared. So this is one of my pieces. This is another piece. This is another piece. This is another piece, and I substitute all those pieces in. Okay. So multivariable chain rule is not going to be kept on the board much longer. We'll see how much longer it can survive. We have our expansion, and now we just need to substitute. The whole point of doing it this way is everything you need is now explicitly written on the board and you're looking at it. So I need to know what df dx is at G of R theta. Oh, that's it right here. I need to know what is dx dr at R theta. It's right here, it's cosine theta. Everything is there. When I have to substitute, I get dA dr. All right, here goes. So df dx at R theta is going to be cosine of R squared minus 2R squared cosine theta times sine R squared. Yes. And then I multiply that by cosine theta, because that's dx dr, right? And now the next part is I have df dy, that's going to be a negative sign. It's going to be negative 2r squared cosine theta, sine theta, sine of r squared, sine of theta. All right, let's start multiplying everything out. So the first piece, cosine theta hits this, I'm going to get cosine theta, cosine of r squared. The next piece, 2r squared cosine theta, that should be a cosine squared theta. So what should I get when I multiply this out, the second piece? So when I multiply by cosine theta, it should be 2r squared cosine cubed theta sine r squared, right? So 2r squared cosine cubed theta sine of r squared minus 2r squared cosine theta sine squared theta sine of r squared. Let's do some algebra. Do you notice anything in common with the last two terms? What do they have in common? What do we have that both have?
2r squared.
They've got more than just a 2r squared. 2r squared, what else? They have that, and they have one more thing in common. They both have a cosine theta. So the first piece is just cosine theta, cosine r squared. And then we can take out a minus 2r squared cosine theta sine of r squared. And we'll have a cosine squared, and we'll have a sine squared. What's cosine squared plus sine squared? 1. And that does match what we have up above. If you look all the way at the top, the cosine of theta times cosine r squared minus 2r squared cosine r squared. I just didn't pull out the cosine theta for both of them. So we have the right answer. It should be clear that for this particular problem, it's much better to just do the direct substitution. But it's nice to see the chain rule work, and it's nice to see a methodical way to get it. If you include all the steps, you greatly minimize your chance of making a mistake. You write down, where am I evaluating the functions? You have your conversion sheet. Here's my list of everything. Here's the values of everything. And now I just substitute in. When you have it all written on the paper, you're much less likely to make a mistake. It's probably the typo. Let's check. So DADR. Yes, that is a typo. So actually, it's very clear because I found a mistake. So thank you. So this should be a sine of r squared. And when we're doing the product rule, the derivative hits r, so you get 1 times cosine of r squared. And then r times the derivative should become a sine. So good catch. And that's the other reason why you do something like this is when you see that they disagree, at least one is wrong. Hopefully exactly one is wrong. And if you can then fix them and match. Any questions on the chain rule? So what I want to do for the last few minutes is do an integration by parts example to just illustrate again the idea of methodically writing down all the steps. Because if you write things down in a good, clean way, you will minimize the chance of making a mistake. So let's say I want to integrate from 0 to 1 x cosine of x dx. So sadly, I don't know a function whose derivative is x cosine x. Well, I know the integration by parts. If you go from 0 to 1 of u dv is uv at 0, 1 minus the integral from 0 to 1 of v du. And the goal is to write things out very carefully. Here is my u, here's my du, here's my dv, here's my v. And by writing everything out clearly like this, I minimize my chance of making a mistake. I then have my table. I've written out the uv formula over here, and I just have to substitute. Now I have a couple of choices. I have x and cosine of x. What should u be? What should v be? So I have two choices for you, basically. What are the two choices for you? X or cosine of x. So imagine you choose one and it doesn't work. And you try one of them and the problem just doesn't work. You go, ah! And you give up in frustration. Now what do? Try the other. It's really nice. There's only two choices. Yes.
Why would you like make one? Like, why would you substitute it for x when you just use x?
Well, this is just how we're doing integration by parts. Here's my u, here's my dv. I could give you a more complicated one. I could give you x squared or x cubed or something like that. Mm-hmm. This is a particularly easy one over here to minimize how much time I'm at the board. You know, for this one, you are right, u is just going to be x. But for a more complicated problem, it's not going to be just x, it'll be more involved. And this way, we're using always the same language. You don't want to do x dv, it's always u dv. The more times you do it the same way, the less likely you are to make a mistake. Now, if we saw that one way wasn't working and we tried the other way and it doesn't work, now we're in trouble. Then you go back to the first one and say, well, maybe the first one wasn't so bad. Maybe there's a way to make that work. So by taking x here, then du becomes just dx. And I've decreased the degree of x. That's great. If I had put x over here with dv, then v would be x squared over 2. I'd be increasing the degree. I'd be making things worse. So when I look at it like this, it strongly suggests that I want the u to be x. And then the dv will be cosine of x dx. So v would be sine of x. And now when I do my integration, I would get uv is x sine of x at 0 and 1 minus the integral from 0 to 1 of v du, which is just sine of x dx. Oh, well, this isn't too bad. At 1, x sine of x is just sine of 1. And at 0, it's just 0. What function has derivative sine of x? Negative cosine. Well, you say, well, since negative cosine has derivative sine of x, but I've got negative sine of x, let me just find the antiderivative of negative sine of x. Let me bring that negative sign inside, and then this would just be plus cosine of x at 0 and 1. And so you would just get the sine of 1 plus the cosine of 1 minus the cosine of 0, which is just 1. So this is your integration by parts, doing it very slowly, doing it very carefully, not skipping any steps. We're creating essentially a nice little dictionary, a lookup table of all the different things we need. And now when it's time to substitute in here, I know what everything is. It's longer to do it this way than to just write down immediately what the answer is, but you're less likely to make a mistake. I wanted to make the problem a little bit harder. Any questions on this before I make it a little bit harder? Okay, so what we're going to do is I'm going to take a more involved integral. So I'm going to give you now the integral from minus infinity to infinity of x squared e to the negative x squared dx. And so I want to do my integration by parts. And so I have to figure out what is my u, what is my v. So any thoughts about what would be a good choice for u? What's a good choice for you? It's okay if it doesn't work, but something to try. So we could try e to the negative x squared. Then when we take the derivative, we'll get negative 2x e to the negative x squared dx. dv would be x squared, x cubed over 3. And so unfortunately, when we do this, we start off with an x squared, we're going to end up with an x to the 4th. It's a good thing to try, but it went the wrong way. All right, take 2. U equals du equals, if at first you don't succeed, what could we try for u? X squared. We try x squared, 2x dx. Okay, this is good. The power is going down. Unfortunately, dv is now e to the negative x squared dx. And that doesn't have a nice antiderivative. Are we out of luck? Or is there another choice for you? I'm sorry? But that's not going to really change anything. It's only going to change the sign. So u, du, dv. We need another choice. So much of math is algebra and finding the right way to look at things. What function are we trying to integrate? What function are we trying to integrate?
X squared e to the negative x squared.
I'm going to write this in a slightly different way. Okay? X times x times e to the negative x squared. You've tried x squared as u. You've tried e to the negative x squared as u. Can you come up with something else to try? I'm sorry? Yeah, just try x. And then du would just become dx. dv is e to the negative x squared, x dx. Oh, yay! E to the negative x squared wants to have an x playing around with it. And then when I integrate, it will become negative 1/2 e to the negative x squared. And it turns out we actually can compute the integral from minus infinity to infinity of e to the negative x squared dx. We will see how to do that later in the semester. This is one of the most important integrals in the world. It's related to the normalization constant of the standard normal of a Gaussian. It's related to the square root of pi. The trick here is I have 3 factors. I could choose x for u, I could choose e to the negative x squared, I could choose x squared, or I could choose x e to the negative x squared. I have more choices than I might have thought. And so I don't have to keep the 2 x's together. And if you look at it, e to the negative x squared, it's great to integrate that, because when you integrate that, you get to use an x floating around with it, and then that power of x now vanishes. You want to differentiate x powers of x, because then when you differentiate, the power will get smaller. Okay, so this is a good place to stop.